Okay, so we are looking at Module 1, Inquiry Question 2, and we're going to look at dot point number 5, which in this case is to analyze the relative motion of two objects in 2 dimensions relative to another. We'll have a boat flowing through a river across a bank, 2 moving cars, and an aeroplane in a crosswind relative to the ground. Okay, so we're going to compare those two. Now, the first thing is to note, the previous recordings that I've done was about the 2 moving cars. And we said that for the 2 moving cars, because we had 2 moving objects, we were using vector subtraction. Okay, because it was 2 moving objects. Alright. When I go to the other scenarios that we're looking at today, which this case will be the river flowing along a bank. A bank is just, as you can see here, just solid ground. And we know that, relatively speaking, the bank is stationary. Now, what we know is if we're trying to compare the motion of a stationary object for the ground to a moving object, we can simply use vector addition. So there is a slight subtlety here. I did say if we're comparing relative velocity, we use vector subtraction. But in the case where we are dealing with a stationary object, we can simply use vector addition. So let's have a look at this. There are 2 types of scenarios when it comes to a boat on a river in terms of relative velocity that we can look at. Scenario 1 would be the velocity of the boat relative to the ground, in which case we can use vector addition. And then we can use vector subtraction if it's comparing the velocity of the boat relative to the river. Now, say for this, we have a scenario, or even the diagram we have below. We have a person standing on the bank, so on the path, and we have a boat coming across down like this, okay? And we have the water going along in that particular direction, okay? So what would happen is, relatively speaking, the person on the bank would see the boat moving down this particular direction, okay? So for this person looking at where the boat has gone, the boat has started from, in this angle here, gone to this part here, okay? And that you can see is the positive velocity of the boat. That's the positive velocity of the river. As a stationary observer, you will see a vector addition of those two coming together. If we were to do something slightly different, we were comparing just the water and the boat, you can see something slightly different. So the boat is here, it's coming down. We have the river going, or the water going this way, okay? If we want to look at what's the boat's relative velocity to the water, okay, according to the water, it's this vector arrow that we see here. Because what's happening is as the boat is going further and further down, the water is going further and further across. So it'll look like this diagonal line gets bigger and bigger and bigger across like that. So eventually, if we just imagine, let's say the boat was the stationary object, it will look like, diagonally speaking, the water is getting further and further away from it. So that's kind of how we can use the two. What we're going to look at later on is one of the questions will be, if the boat is traveling across like this, because the river is pulling it along like that way, at what angle should we travel in this particular direction in order to go directly across the river? So we'll come back to that in a second. First things first, we have a couple of questions. And do note what's the question asking. It's asking you the relative velocity to the ground. So you're looking at this simply through the lens of vector addition. So you have a boat that's moving north, at 5 meters per second, and you have a current flowing downstream 2 meters per second east. Okay, so if we're the stationary observer, okay, so we're on either side of the bank, on this side or that side, you'll see that the resultant vector of the boat gets carried across in this particular direction along this here. So our resultant velocity is 5 squared plus 2 squared equals 2. If I just get my calculator out, about 5.39 meters per second, rounded off to 3 sig figs. If I look at the angle, okay, that's my adjacent side, that's my opposite side. So I use inverse tan, or tan inverse, 2/5. I get about 21.8 degrees. So in this case, the direction is north, 21.8 degrees east, moving at a velocity of that there. Okay, so that's the velocity of the boat relative to the ground as we see it. Why do we see it like that? Because obviously the current here is dragging the boat along, and so that includes an additional part of how fast the boat is traveling. So there's that. Now question 2 goes through a very similar question or similar idea, so I'm not going to go through it entirely in terms of the calculations. You can see it in a second. But if I was to draw it out, our boat is going south, 3.8 meters per second, and then the stream is flowing west at 2 meters per second west. And so the resultant direction is this one, and theta would be this one here, because remember, theta is always where the arrow starts. And so for question 2, if you got 4.29 meters per second south, 27.8 degrees west, that was the correct answer. Let's look at something slightly different. This time we're going to look at the relative velocity to the water. Okay, so the river flows south to north, so south to north, so it's going this way, okay, at 0.4 meters relative to the shore. So if I'm just standing by the shore, it looks like it's going at 0.4 meters. What must the boat's velocity relative to the water if it is going due west? Okay, so it's going due west, so it's going west this way at 2 meters per second. Okay, so the question is, what is the velocity, or what's the relative velocity between the water and our boat, if these were the movements that we see here? Okay, so if we have a look, again, this one looks like a vector addition. So if we draw it along across here, 2 meters per second, theta's there. Okay. Okay, let's just clear this out for a second. Just made a little error, but let's just draw it out again. So we have a river, and it's flowing south to north, 0.4 meters per second. And then we have a boat that is going 2 meters per second west. Now, because this is between two moving objects we are looking at the relative velocity of the boat to our river or water. Okay, so it would be boat positive subtracted by the negative vector of our water. In this case, if we draw it out, that would mean that we have the positive movement of our boat and the negative movement, or the negative velocity component of our water. Okay, so the angle we get is theta here. This is 2 meters per second, and over on this side, that is 0.4 meters per second. So this component, the resultant component, is just 2 squared plus 0.4 squared. 2 squared plus 0.4 squared. So we have a relative velocity of 2.04 meters per second, rounded off to 3 sig figs. And then if we look at this in terms of the angle, tan theta, we have 2 at the bottom, 0.4 at the top. And we have an angle of about 11. So in this case, our net velocity, or not our net velocity, but the relative velocity we have is 2.04 meters per second at an angle of west 11 degrees south. So that's the movement that we see here. Like I said, because these two objects are moving away from each other, you can picture that afterwards the boat has gone here, the water after the second has gone here. So the question is, what is the difference from the boat to travel all the way here, or the water to travel all the way there? Then to work out what the angle is. To work out that angle, you can just go back to your vector subtractions. Question 4, this one we can actually test out using our simulation. It says the river is 350 meters wide and the stream in its flow is 7 meters per second. Calculate the direction relative to the stream the boat needs to travel if it was to reach the bank directly opposite to its starting point. Okay, so let's have a look here. The length we have of the bank is 350 meters. Okay, and the stream is flowing at 7 meters per second. So, I don't really think it really matters at this point in time how long it takes, but 7 meters down or up. So it says, which direction relative to the stream would a boat need to travel if it was to reach the bank directly opposite its starting point at time 35 seconds. Okay, so let's work out how long it will take in terms of velocity to get across the stream. So we want to work out how fast are we trying to move to get across 350 meters in 35 seconds. So the velocity is 350 meters within 35 seconds. So that should be about 10 meters per second. Okay, so we need to travel 10 meters per second to reach that mark there. Okay, so what we have here is 10 meters per second here, and the stream is flowing 7 meters per second like that, which means the boat is going at this angle down this way, assuming we're saying it's flowing downstream. So let's just say assuming river flows downstream. Okay, so that means that this is the resultant velocity we need to travel to reach the other side at 35 seconds. But this is also the angle we will have to travel in opposite later on to reach the other side. So our resultant velocity is 10 squared plus 7 squared, rooted Okay, and that is about 12.2 meters per second. Tan theta, or theta is tan inverse of 7/10, and that gives us a number of about 35 degrees. So if I'm assuming this is flowing downstream, or this is the east direction, that's the north, south, west. The stream is currently, or the boat is currently going east 35 degrees south. Okay, so that's where it would push my boat if it was to go directly across. So what can we do here? So to move directly across, we need to go at the opposite of that angle. So the boat needs to travel 12.2 meters per second at an angle of east 35 degrees north. Okay, I want you to picture it this way. Get a little change in color. So the boat is trying to travel across this way. If the river was flowing downstream, our boat is going to be carried across down here as the resultant motion. So the only logical method is to have the boat moving at that same velocity, but this time at the exact same angle, but in the opposite direction. And so what you'll see is, if doing it like that, the boat will just go directly across the river. Okay, so there is that. Okay, so the final little thing I just want to look into is what if they don't give you the stream or stream numbers or whatever. So the question is, if we want to go directly across like here, okay, and these are some of the settings that we found. So the river is going at 3 meters per second in that particular direction. And the constituents we have is the velocity of the boat relative to the river. We said that this component, so that's the diagonal. So whenever you hear the line boat relative to river, it's a diagonal line you're looking for because that's the resultant vector of that. Okay, so it's not this vertical line. It's not going to be a straight line. It's going to be one of the horizontal lines that you draw out. Okay, and that is at 4 meters per second. So theta is this angle here. So the idea is, at what angle must I move the boat in order for it to go straight across? So if we use theta, we have the opposite side and we have the hypotenuse. So we use sine theta, or inverse sine. The opposite side is 3. The hypotenuse is 4. So if we have a look, 3 divided by 4, okay, according to this, the angle, okay, the angle that we need to travel is 48.6 degrees. So that's the angle created from this motion, which means, if assuming that this direction is north and this direction is east, if we go directly across, the river is going to drag our boat north 48.6 degrees east. So if I want to go directly across using these settings that were given to me, I would need to travel at 48.6 degrees northwest in order to go directly across. So that's what we'll look into now. Okay, so the settings that we have, we said that the velocity is 3 meters per second for the velocity of the river relative to the Earth, so going that way. And the velocity of the boat is 4, so it's this bit going here. So we said that the answer was 48.6 degrees. So if this was to travel directly across, the angle that's being caused here to go diagonal is 48.6 degrees. Okay? Which means that if I want to go directly across in this direction, or directly across like this, sorry, I would need to travel in the opposite direction at 48.6 degrees. Okay, so this is my setting here, 48.6 degrees west of north, so north 48 west like that. So if I now run my simulation, you should see, based on the calculations I just did, the boat should go directly across the river now. Okay, and let's see if it gets there. You can see, and it reaches the other side like that. Okay, and that's exactly how you do that question there. Anyhow, if you have any other questions related to relative velocity or the fundamentals of it, go back to the very first video of this series of relative velocity components. If you want to look into scenarios about aeroplanes and all that, that will be the next video that's coming along. So anyhow, thank you for staying along for so long, and have a nice day.